In a photoelectric effect experiment, a UV light of certain intensity is shown onto metal sample A to produce an electric current. The work function of metal A is 4 EVs. In a second experiment, the same UV light of the same intensity is shown on metal sample B with 3 EVs of work function. Which of the following is correct about the second experiment? A. There is no electric current produced in the second experiment. B. The wavelength of the incident UV light is needed in order to decide whether there is an electric current in the second circuit or not. C. The cutoff frequency is needed in order to decide whether there is an electric current or not. D. The maximum kinetic energy of the ejected electron is higher than that in the first experiment. E. The stopping voltage is lower than that in the first experiment. Because sample B has a lower work function, it takes less energy to eject an electron. There is a current produced in the first experiment, so there must also be a current in the second experiment. Therefore, A, B, and C are all wrong. Because the maximum kinetic energy equals to the HF of the incident UV minus the work function, the lower the work function, the higher the maximum kinetic energy. So the answer is D. For E, the stopping voltage is used to measure the maximum kinetic energy, and the maximum kinetic energy equals to Q times V, E times the stopping voltage. So when the work function decreases, the maximum kinetic energy increases, and the stopping voltage also increases. So E is wrong. By the way, the cutoff frequency is related to the work function. The work function equals to the h times the cutoff frequency because the minimum photon energy required to eject an electron equals to the work function. So if we know the work function, we know the cutoff frequency. Both the work function and the cutoff frequency are the properties of the metal sample. In an experiment, a beam of monoenergetic electrons is incident on a pure gas. It is found that the gas atoms are excited if the kinetic energy of each electron in the beam is 3.2 EVs or greater. Once the gas atoms are excited by the 3.2 EV electrons, they emit photons of a single wavelength. When the kinetic energy of each electron in the beam is increased to 5 EVs, 2 additional wavelength photons are emitted by excited atoms. Which of the following photon energy cannot be among the photons emitted by the atoms excited by the 5 EV electrons? An electron inside an atom can transition into a higher energy state by absorbing a photon, by absorbing the energy of another energetic electron, or by the heating of the atoms. When the atoms are heated, the collisions between the atoms can cause the atom's electrons to be excited. In this problem, energy transitions are caused by absorbing the energy of other energetic electrons. When this happens, the energetic electrons can have more energy than the energy difference between the upper and the lower energy levels, because the incident electrons do not have to lose all of their kinetic energy to the atoms. And since the gas atoms can be excited by electrons with at least 3.2 EVs of kinetic energy, the energy difference between the two states of the transition must be 3.2 EVs, and the lower of the two energy states must be the ground state. So the single wavelength photons given off by those excited atoms must be 3.2 EVs as well. When the kinetic energy of each incident electron is increased to 5 EVs, 2 additional wavelength photons are emitted by the excited atoms. This means there must be another energy level that is 5 eVs above the ground state. So the excited atoms can go through 3 different transitions. Straight down to ground state, or down to here and then down again. So the energy of the photons emitted can be 5 eVs. 5 minus 3.2 equals to 1.8 eVs and 3.2 eVs. So the energy cannot be 8.2 eVs. The answer is D.